Alright, let's go. Number 10. LB1. The black hole that broke the rules. For decades, astrophysicists operated under a firm and mathematically certain rule. Stars born in our galaxy cannot collapse into black holes larger than roughly 20 to 25 times the mass of our Sun. The reason is simple. When a massive star dies, it detonates in a supernova, ejecting the vast majority of its own mass outward at thousands of kilometers per second. What remains behind is a modest stellar corpse. The physics of stellar winds and mass loss ensures that by the time a star dies, there simply is not enough leftover material to produce anything larger. That was the rule. Then, in 2019, a team of Chinese astronomers using the Lamos telescope announced the discovery of LB1. At the center of this system sits a black hole with a mass of approximately 70 times that of our Sun, located roughly 15,000 light-years away. It had been hiding in plain sight. A black hole that, by every model of stellar evolution we possess, should be physically impossible to create inside the Milky Way. The star orbiting it completes one revolution every 79 days. The data is unambiguous. Something is there, and it is far too massive to exist. Scientists have proposed revisions. Perhaps the mass estimate is slightly off. Perhaps two smaller black holes merged. But no clean explanation has survived full scrutiny. LB1 sits in our own galaxy right now, defying the mass limits that stellar physics spent a century establishing. It is not supposed to be there. It does not care. Number 9. Przybylski's star, the radioactive impossibility. Stars are predictable. That is one of the most useful facts in all of astrophysics. Given a star's mass, age, and composition, you can calculate its spectrum with extraordinary precision. You know exactly what elements will be present. And then there is Przybylski's star. When astronomer Antoni Przybylski analyzed this object in the constellation Centaurus in 1961, he found a spectrum that violated every expectation simultaneously. The star is almost completely missing iron, one of the most abundant elements in the universe. In its place, the atmosphere is saturated with ultra-heavy radioactive elements: promethium, actinium, and most disturbingly, einsteinium. Einsteinium does not exist in nature on Earth. We can only produce it inside high-energy particle accelerators. More critically, einsteinium-253 has a half-life of just 20 days. In astronomical terms, 20 days is nothing. For these isotopes to remain continuously detectable, something must be actively manufacturing them right now at a rate that compensates for their constant decay. No known stellar process does this. The mainstream hypothesis points to the theoretical island of stability, a predicted region of super-heavy elements that might resist decay. But that island has never been confirmed to exist. The alternative, which the data does not rule out, is that the chemical signature of Przybylski's star looks less like a natural stellar atmosphere and more like something was deliberately put there. Number 8. EGSY 8P7. The galaxy that existed too early. The Big Bang happened 13.8 billion years ago. In the first few 100 million years, the universe was a dark, featureless fog of hydrogen gas. No stars, no galaxies, no light. Slowly, gravity pulled matter together. The first stars ignited. The first primitive galaxies began to form. This process takes time. Enormous amounts of time. The physics of gravitational collapse sets a firm lower bound on how quickly a mature, luminous galaxy can emerge from the primordial darkness. Then the Hubble Space Telescope found EGSY 8P7. We are observing this galaxy as it existed just 600 million years after the Big Bang. At that point in cosmic history, the universe should still have been largely opaque, filled with neutral hydrogen gas that blocks ultraviolet light and prevents a clear intergalactic medium from forming. EGSY 8P7 is not just present at this impossibly early moment. It is massive. It is luminous. It is already producing stars at a ferocious rate. And it is emitting high-energy ultraviolet radiation that should not be able to travel through the fog that was supposed to still dominate the universe at that epoch. For this light to reach us, the galaxy must have already carved out a massive ionized bubble in the surrounding intergalactic medium, a bubble that, according to our models of cosmic reionization, should not yet exist. EGSY-8P7 matured billions of years before the universe was supposed to allow it. Number 7. The OMG particle. Physics at the breaking point. On the evening of October 15, 1991, a detector array in the Utah desert registered something that should not exist. A single subatomic particle, a proton, arriving from deep space at a velocity so close to the speed of light that the difference was negligible. When physicists calculated its energy, they arrived at a number that stopped the room. 3.2 times 10 superscript 2 electron volts. The most powerful particle accelerator humanity has ever built, the Large Hadron Collider at CERN, accelerates protons to energies of roughly 6.5 tera-electron volts. The OMG particle carried energy approximately 40 million times greater than anything we have ever artificially produced. But the problem is not just the energy. At energies this extreme, a phenomenon called the GZK limit applies. Ultra-high-energy cosmic rays traveling through space interact with the cosmic microwave background radiation, the faint afterglow of the Big Bang, and lose energy over distance. At these energy levels, the particle could have traveled no more than 160 million light-years before slowing below the detection threshold. We have found no obvious source within that range powerful enough to produce it. The particle arrived. Its source remains unidentified. The mechanism that accelerated a single proton to 40 million times the power of the LHC remains one of the most disturbing unsolved problems in all of physics. Number 6. Tabby's star, the dimming that defies explanation. When the Kepler Space Telescope monitored stars for the subtle periodic dimming caused by orbiting planets, it expected clean, repeating signals. A planet crosses. The star dims by a small, predictable fraction. The planet moves on. The star returns to baseline. Simple, mechanical, predictable. KIC 846-2852, also known as Tabby's star, does none of these things. Between 2011 and 2013, Kepler recorded dimming events so irregular, so extreme, and so structurally bizarre that researchers spent years ruling out instrument error before accepting the data was real. The star dimmed by up to 22%. No single planet produces a dimming event anywhere near that magnitude. The events were not periodic. They were not symmetric. Some lasted days. Some lasted weeks. Furthermore, long-term photometric records going back over a century show that Tabby's star has been gradually fading at a rate no known natural stellar process produces. Dust clouds have been proposed. Swarms of comets have been modeled. None of the natural explanations survive full scrutiny against the complete data set. The hypothesis that received the most attention, a megastructure built by an advanced civilization to harvest stellar energy, was not proposed by fringe theorists. It was raised in the original peer-reviewed paper by the Discovery team themselves as a possibility they could not eliminate. The star continues to dim unpredictably. The cause remains officially unknown. Number 5. J0529-4351. The black hole that eats a sun every day. Black holes grow by consuming matter. But physics imposes a strict speed limit on this consumption, called the Eddington limit. When matter falls toward a black hole, it forms a superheated accretion disk that radiates enormous energy outward. If the black hole tries to consume matter too quickly, the outward radiation pressure overwhelms gravity and physically blows the infalling material away. The black hole chokes. This limit is one of the firm constraints on how fast these objects can grow across cosmic time. Then astronomers re-examined archival data from the European Southern Observatory and identified J0529-4351. At its center sits a quasar, an actively feeding supermassive black hole, consuming matter at a rate equivalent to approximately 1 solar mass every single day. It is the most luminous object ever identified in the known universe. So bright that, despite sitting 12 billion light-years away, it could theoretically be detected with a sufficiently sensitive amateur telescope. The black hole contains a mass roughly 17 to 40 billion times that of our Sun. The accretion disk feeding it stretches across 7 light-years of space, a structure so vast it would span the distance from our Sun to the nearest stars. The rate of consumption does not merely approach the Eddington limit. It appears to violate it. How a black hole feeds at this rate without destroying its own food source remains an open question that current models of accretion physics cannot answer. Number 4. The cold spot, the bruise on the universe. The cosmic microwave background is the oldest light in the universe. It is the faint thermal afterglow of the Big Bang itself, radiation that has been traveling freely through space for 13.8 billion years. When satellites map this radiation across the entire sky, they find an almost perfectly uniform temperature with only tiny fluctuations of 1 part in 100,000. These fluctuations are the seeds of all structure in the universe, the original density variations that gravity eventually amplified into galaxies. They should be random, statistical, without large-scale patterns. In 2004, astronomers analyzing data from NASA's WMAP satellite found something that violated this expectation entirely. A region of the sky approximately 1.8 billion light-years across, where the cosmic microwave background temperature is measurably and significantly colder than everything around it. The cold spot. At this scale, a natural random fluctuation producing a temperature deviation this large has a probability of approximately 1 in 50,000. Subsequent analysis confirmed that the cold spot corresponds to a genuine supervoid, a region of space containing significantly fewer galaxies than the surrounding universe. But even accounting for the void, the temperature anomaly is larger than standard cosmology can explain. One hypothesis proposed seriously in peer-reviewed literature is that the cold spot is the imprint of a collision between our universe and a parallel universe, a bubble collision from the era of cosmic inflation, leaving a permanent bruise on the oldest light in existence. Number 3. NGC 1277, the galaxy devoured by its own core. In a standard galaxy, there is a relationship. The central supermassive black hole and the surrounding stellar population maintain a predictable ratio. The black hole typically contains roughly 0.1% of the total mass of the galaxy's central bulge. This relationship holds across thousands of galaxies of wildly different sizes, ages, and environments. It is one of the most consistent scaling relations in all of extragalactic astronomy. NGC 1277 breaks this relationship so completely it reads like an error. Located 220 million light-years away in the Perseus cluster, this compact galaxy contains a central black hole with a mass of approximately 17 billion solar masses. The black hole accounts for roughly 59% of the total mass of the galaxy's central bulge. To put that in perspective, if the Milky Way followed the NGC 1277 ratio, our central black hole, instead of its actual mass of 4 million solar masses, would be roughly 50 billion solar masses. So massive its event horizon would extend beyond the orbit of Uranus. NGC 1277's black hole is so disproportionate to its host that the galaxy should not have been able to form around it in any configuration our models predict. The black hole consumed or ejected the gas that would have formed stars before the galaxy could reach a normal size. It is not a galaxy with a large black hole. It is a black hole wearing a galaxy as a thin shell. Number 2. The Boötes void, the emptiness that should not exist. Structure in the universe follows a pattern. Matter clumps. Gravity pulls galaxies into groups, groups into clusters, and clusters into filaments and sheets. The vast cosmic web that spans everything we can observe. Between the filaments lie voids, regions of relatively low density. But the physics of cosmic structure formation sets limits on how empty and how large a void can be. The largest voids produced naturally by standard cosmological models extend to perhaps 300 to 400 million light-years across. In 1981, astronomer Robert Kirshner and his colleagues were conducting a galaxy survey in the constellation Boötes. They expected the usual distribution. What they found instead was nothing. A region of space approximately 330 million light-years in diameter, containing almost no galaxies whatsoever. Where hundreds of galaxy clusters should have existed by statistical expectation, there were approximately 60. The Boötes void is so empty that if the Milky Way had been located at its center, we would not have discovered the existence of other galaxies until the 1970s. The universe beyond our local group would have been invisible to us for most of human history. What disturbs cosmologists is not just the size, but the shape. Naturally forming voids are irregular, shaped by surrounding filaments pulling matter away unevenly. The Boötes void is suspiciously spherical. No mechanism in standard cosmology produces a void this large, this empty, and this geometrically clean. Number 1. The axis of evil, the universe that knows we are here. The cosmological principle is the bedrock assumption of modern physics. It states that the universe has no preferred direction, no special axis, no center. On large enough scales, everything looks the same in every direction. Without this principle, the entire mathematical framework of modern cosmology, dark energy, dark matter, the expansion of the universe, collapses. It is not optional. It is foundational. In 2003, astronomers analyzing the first detailed all-sky maps of the cosmic microwave background from NASA's WMAP satellite found a pattern that should not exist. The largest scale temperature fluctuations in the oldest light in the universe, structures spanning billions of light years, were not randomly oriented. They were aligned. Aligned with each other. Aligned with the plane of our solar system. Aligned with the direction of Earth's motion through the universe. This alignment has been called the axis of evil by cosmologist João Miguel, not as hyperbole, but as a precise description of what it means for physics. The probability of this alignment occurring by chance in a truly isotropic universe is less than 0.1%. The European Space Agency's Planck satellite, a more sensitive instrument launched specifically in part to verify this finding, confirmed it in 2013. The alignment is real. It has not gone away. The explanations range from undiscovered instrumental errors to exotic modifications of inflationary cosmology, to the deeply unsettling possibility that the large-scale structure of the universe is somehow oriented relative to our position within it. If that last possibility is correct, the cosmological principle is wrong. And if the cosmological principle is wrong, then almost everything we believe we know about the origin, age, and ultimate fate of the universe must be rebuilt from the ground up. If you want to see more videos like this, click the video on screen now and make sure to subscribe.